So thank you very much, Benjamin, for offering your time to give us Canadian some nice information on borehole geophysics. So I will give you a little bio of Benjamin. We don't know each other, so as I said, I will read some of your LinkedIn profile here. You did both your bachelor and PhD in physics and radiometry in Queensland, University of Queensland, yeah. And then worked for 4 years, 2 years at Schlumberger as a petrophysicist. And then you said that you did 4 years in Ottawa with the GSC. Is that what you said?
With the NRC.
With NRC.
Yeah.
Very well. So again, thank you for joining. Without further ado, the floor is yours. I will mute myself and be quiet.
So good afternoon, everyone. So yeah, thank you for the opportunity to present today. So today I am going to introduce Borehole Magnetic Resonance. I believe most of you have seen or heard of this technology before. So I will sort of run through a quick bit of theory, introduction on how the measurement is made, look at a sort of a workflow of the process from collecting the data to sort of getting a basic interpretation that we can then use in different applications. And I'll show you a couple of quick snapshots of those applications. So borehole magnetic resonance uses the principle called nuclear magnetic resonance. And this is the same technology that's used in places in hospitals for magnetic resonance imaging and chemical spectroscopy. So just different size magnetic fields, but the principle and the physics behind the measurement is the same. So the principle behind the measurement is called nuclear magnetic resonance, and it gets used in hospitals and chemical spectroscopy and a few different other regions. So basically it uses a magnetic field and some resonant frequencies to get a signal from your target nucleus that you're looking at. So borehole magnetic resonance is our company's name for it, but there are others out there as well. And it is a tool that we can connect to a standard wireline, 4-core cable or 7-core cable, and run it down a hole to collect data as per any sort of wireline logging tool. There's no chemical sources, there's no radiation, it's just sort of a magnetic material and some antennas to collect a measurement. So what does the technique give us? So it gives us a range of information, and some of these are lithology independent answers. So when we take our measurements, and I'll explain how these are done very soon, we get things like total porosity, and we get what we call a T2 distribution. And I'll explain some of these terms in the next couple of slides. And once we sort of have this base measurement here, we can then go on and do things like some lithology dependent interpretation. So we can get things out like our free water volumes or our bound water volumes and start calculating permeability and hydraulic conductivity. And all of this is great as a single tool measurement, but the real power, I guess, from any geophysical measurement comes from combining all of our other data streams. So if we have density measurements or resistivity measurements, we can start doing things like a salinity analysis of your aquifer, or you can calculate things like a dry weight density or a dry bulk density. So all important inputs to your resource model, depending on what that resource model is. The other couple of beauties of the BMR tool is that there's no chemical sources. So it's things like density or neutron porosity, they require a radiation source. So if you're concerned about that, that is an extra step. And if you go through the calibration process and everything like that, you can start looking at it a way to replace things like your pump tests and packet test because we can use it to get a continuous log of hydraulic conductivity. So, as sort of mentioning before the meeting started, this technology has come from the oil and gas industries from the 70s because they wanted to work out how much oil was in their reserves, in the ground, in the rock matrix. So, you know, there's been us and a couple of other companies that have looked at moving it out of that area, and to date we've sort of covered a few different environments from hard rock mining to in-situ recovery, so things like potash, lithium, uranium, some normal oil and gas, coal seam gas logging, and have worked for, you know, different groundwater departments and everything like that. So what is magnetic resonance? So we target hydrogen in a liquid or gas form. So this is H2O or in a carbohydrate sort of environment. So typically the hydrogen atoms we can think of as a simple sort of magnetic dipole moment. So they have a magnetic bar to them. We expose them to a static magnetic field, and over time they will all polarize to that orientation. And then we can interact with these polarized nucleuses, and the simplest form is to turn that magnetic field off, and over time they will go through this dephasing process. And how the amount of time it takes to polarize is related to this term T1, which is called the spin lattice relaxation rate, and how quickly it dephases is related to this spin-spin relaxation rate, or T2. And this is the main measurement that we take, is trying to determine what this T2 time is. So our measurement sort of looks something like this, where we do a series, we do a special sequence called a CPMG sequence. And out of that, we get these little red dots as our measurements, and they're our amplitude of our echoes. We do a series of rephasing. And the most simplest measurement that we get out of it is our total porosity. So where our green curve comes back and crosses the y-axis is our total porosity. So this is sort of a lithology, it is a lithology independent measurement of total porosity because it's physically measuring all of the water molecules trapped within the pore space. We don't look at any of the hydroxyls in the clay minerals or anything like that. It is just purely the water within the pore space. This decay is very hard to look at, but mathematically we know what that is, and we can convert that to a T2 distribution, which we have here down in the bottom section. So we get a T2 distribution. And then this gives us a lot of powerful information because we can think of it as a pore size distribution. And we can get this as a continuous measurement up the length of the borehole. So what do we physically measure? So the name magnetic resonance tells us everything that we need to know about the measurements. We have a magnetic field. If we look here in this diagram on the left, as we get further away from the tool, our magnetic field strength decreases, and we have resonance. So it's a frequency dependent event. So if we tune our transmitter to a particular frequency, we only receive signals from a very small measurement zone. And then if we move that into a three-dimensional space, we sort of get a sensitive shell around our tool. So as long as there's no metal between the tool and the shell, we can get a measurement. So we can log in things like open hole, PVC, or fiberglass cased environments. And we can also do things like vary in the workshop, vary where this is positioned. So if we have a known diameter investigation, we target that. So the other critical bit of information for sort of any NMR-based tool is what we call an echo time. So I mentioned before that we have a CPMG decay, and it looks something like this in real life. It looks something like this blue squiggly line. Depending on the interval between our measurements will depend how easy we can fit this decay at this very short T2 times. So depending on how much data we have, we can either estimate our total porosity to be quite high or quite low. All of the tools are designed so that we are at a certain TE value so that we can best estimate these very small, short relaxation times that we often see in clays and iron oxides, things like that. So how quickly this decay moves. Let's move. So let's move that so you can see more of the slides. So how quickly this decay falls down, which is this black line here, is related to a couple of or three major factors for our T2 relaxation time. Two of these are very negligible for the majority of the environments that we work in, and the main driver is a pore size relationship. So if we have very small pores, like in this top left section here, then our decay looks something like this blue line, this brown line down here at the bottom. And if we have really large pores, then the decay is quite slower, so that when we do our inversion, we can get a volume of large pores and a volume of small pores. So now we can consider our T2 distribution as a pore size distribution. So anything that has a short T2 time has a small pore structure. Anything that has a large T2 time has a large pore structure. And then this, then flows on to our hydraulic conductivity and permeability estimates. So, there's a few different methods of determining permeability or hydraulic conductivity within a rock matrix. From NMR, so this goes back to the Cosny-Kármán relationships that related permeability to the surface to volume ratio and the porosity. So when we look at our T2 distribution, we can have a relationship that relates total porosity and in this equation here, and our surface to volume ratio. There's a couple of ways of determining this. So we can either look at it as a ratio between the movable water and the bound water, or we can sort of look at it as the logarithmic mean of our T2 distribution. And then once we have permeability, we can jump down into hydraulic conductivity. So that's sort of the crash course I get in nuclear magnetic resonance, the measurement and how we can start getting some numbers out of it. So the next 15 or so slides, we are actually going to step through that from the data that we collect and sort of come up with a final sort of basic interpretation of some data. So if we're looking at where we can get data for a basic hydrogeological model, historically, everything has been sort of based on cores and aquifer tests and well tests to get the bulk of our data that we need. Some Y-line logging, so basic things can give us some basic porosity information, but a magnetic resonance tool can start giving us information about our specific yield, specific tension, hydraulic conductivity, and because it is a continuous log, we can sort of upscale it to get transmissivity out as well. So what does sort of a completed sort of log looks like? This is a sort of basic sort of workflow that we've developed over the last couple of years. And we combine all of our logs together into a composite log, and we can start breaking out each of the things to get our storage properties, our flow properties, and then we can start looking at things like our water quality as well. And I'll show a couple of examples of why this is important and how it can be used at different phases throughout a project. So we'll start off with the, to a certain, depending on how you want to look at it, some of the basic outputs of the tool. And then here we've got a gamma ray log. So hopefully everyone's familiar with a natural gamma ray. And I know this environment quite well. It's a basic clay sand structure. So low gamma ray sands, high gamma ray is our shales and clays. We have our total porosity measurement here, and we're sort of seeing porosities in the 30 to 50% range. This is an unconsolidated sandstone, so it's basically like sand, beach sand. So we sort of expect quite high values, and then we get our T2 distribution, which is the green bumps, and the black line is our logarithmic mean. What is nice about this example is if we look at this top section where we have a low gamma ray, we have a long T2 time, so we know we've got large pores within this area. Where we have a high gamma ray, we have a lower T2 time. And then once we start getting down to this bottom sort of section here, we'll see a general increase in gamma ray with some thin bedding of some clays and shales. And we see that in our T2 distribution as well. We get like a bimodal effect where we get small pores and large pores within the rock matrix as well. So we're already getting a good qualitative picture of that formation. So the first thing that we're going to start looking at is our defining what is bound fluid and what is free water or movable water, or if you want to think about it as specific retention and specific yield. So a lot of the values that we can use typically comes from literature and are sort of global averages. So the first one that we're going to look at is for sandstones or clastic environments. And this is a value of 33 milliseconds, and it's roughly where this black line is. And we say anything to the left of this is bound water, and anything to the right of this is movable water. And we can just do a hard cutoff of left is bound, right is free water. If we're looking at different environments, so say if we're moving into a carbonate environment, this cutoff can range anywhere from sort of 80 to 120 milliseconds, depending on the limestone or carbonate environment. So now if we compare these two together, we can see that there's a slight increase in our bound fluids through this section here when I jump over, because our T2 cutoff is moving further to the right. So this T2 cutoff, there is a lithology dependence to it. So iron oxides have been seen to be sort of down into the 4 to 10 milliseconds area. So we see a really quick decay and we get a bump out here on the left. And you know, we start with global averages because we know that is a reasonably good place to start and gives us a good answer most of the time. So if we stick with our clastic cutoff, you know, our water volume graph looks something like this, and we can break out a volume of specific retention or bound water, depending on what you want to call it, and then also a movable water or specific yield value. And our total porosity is the addition of those two. This is sort of a oil and gas sort of definition, but is also quite useful because it tells us something about the lithology as well. Is this idea of clay-bound water, so the water that is electronically connected to the clay minerals. It typically has a cutoff of 3 milliseconds. So now if we put our third cutoff in, we start seeing a volume of clay-bound water, a volume of capillary-bound water, and then our volume of movable water. in a sort of a nice simple concept, we merge clay bound and capillary bound to give us our specific retention in this track here, and our movable water remains the same. So it's just a way of giving us an extra indication of how much water may remain within the rocks, and it typically correlates quite nicely with our gamma ray value here on the left. So once we have either our T2 log mean up here, or our volumes of bound water and free water, we can use those equations that I showed you before to calculate permeability and then convert it to hydraulic conductivity. And now we get our two equations for hydraulic conductivity. And these are just using default coefficients, which I show you in the next few slides. But the beauty of this now is that we get a measurement of where our high permeability or high hydraulic conductivity zones are, and where our impermeable layers are in a nice continuous format. So this one doesn't show it as well, but if we're looking at gamma ray only, some of these bands you might think of as an impermeable layer, but when you do the measurement, you'll see that there's still sort of some potential communication between them. And if you're sort of looking at a transmissivity value, we can integrate that hydraulic conductivity log up, and we get this continuous transmissivity flow. So we've worked on some projects where they've used this transmissivity curve to help with their completions of the bore. So they log this in open hole, they complete the well, they do their cleanup process, and they'll run a flow meter, and the flow meter should match this profile, have a similar trend to this profile. If they're seeing a deviation from this, then they know that a certain area of their well has not cleaned up very well, and they'll go back and target that area just to make sure that they can get the well producing as well as the bore producing as well as they hoped for. So that's sort of the storage and hydraulic conductivity properties covered. And we've sort of already looked at a qualitative analysis of our different pore sizes, but we can move from a clay, like a water volume or a capillary volume measurement and our total porosities, and then move that across to a volume of clay, a volume of silt, and a volume of sand. So, and our effective porosity or our total porosity at the end. So now instead of just having a qualitative assessment, we get more of a structural interpretation of the formation. And that's what this track here is called Model 2. There's a couple of just different ways of doing it, and we end up with a volume of clay, a volume of silt, and a volume of sand. And this supports our qualitative model that we did earlier, where we said a low gamma ray is our sands, and we see a high volume of sand in those places. And then high gamma ray is our is our clays and our shales, and we see a high volume of clay and shale, and a low effective porosity because all of the water is bound up within that matrix and within the small pore structure. So some of the other things that you sort of can quickly do at the rig site to give you a good indication of different environments. So there's things like Archie's equations that relate to porosity and formation resistivity to give you a water salinity. And if you know your environment and understand the different coefficients, you can sort of do a very basic salinity measurement. So you can calculate your water resistivity based on a porosity and a deep resistivity measurement. this curve is sort of only valid in certain areas because the coefficients that feed into it are lithology dependent. And you can average over that area to give you a salinity from the log. So the blue line is a log salinity. And then if you're able to do lab measurements, you can get a salinity as well. And in this case, we see some very good correlations between a lab result and the log salinity. And we've got a cross plot here from a couple of different other holes that have been done in the project. And this has been slowly filling up over time. I just don't have the latest plots. And we see some good correlations between our lab results and so the project's lab results and our log results. So now if you're looking at doing a completions, you can start determining and being more selective of what aquifers that you want to use. So if you're looking at a aquifer for agriculture or feeding to livestock, it has different requirements than humans. So you might target different aquifers for your different end needs. It also helps you to determine where you want to set your screens. So you should, if you're trying to optimize your bore, you'll only sort of select screens that will target the aquifer that you're most interested in. So this was part of a research project where they're monitoring different aquifers. So they would do the log and set their piezos in the zone that they were wanting to test and monitor over the next 20 years. And sort of I've mentioned that as well. So the other, come on to that later on. So that is sort of the basic flow of a BMR measurement and a hydrogeological sort of characterization. And we can use the same technique in many other different industries or resource sectors. So here in Australia, brine mining is coming quite popular, or in-situ recovery or leach mining, basically where either the resource is trapped within the fluid or they want to inject chemicals to extract the property out of the rock. And for this, they need to know the porosity and the permeability. So one example where they worked through a full BMR analysis was on one project where they used BMR to help define their resource. So I mentioned before that total porosity and our T2 distribution is a lithology independent measurement. Our cutoff though for our definition between bound and free water is based on the lithology though. So there's a surface relaxivity term rho here, and also the ratio between the surface area and the volume of the pore. And there's sort of global averages related to sandstones and carbonates. So if you want a more accurate answer, you can go through a coring program to determine what this cutoff should be. And this is what this company did. So they went through and did their analysis. So if you're paying attention, there's a hydrogen index correction to some of this data because it's in a very hypersaline environment, which pushes out the water molecules. So we need to correct for that. And we have those measurements quite quickly in the field, so we can produce our logs with our total porosities and things like that. Then we applied our standard cutoff for the area of 33 milliseconds, and the customer was able to go through and do their initial assessment of the reserves. They sent off a series of cores. They came back with those cores. We went through and did the analysis, and basically the analysis involves taking the core plug, filling it full of water, taking a NMR measurement in a lab environment, desaturating it, taking another NMR measurement on it, which is the light blue curve, and you can compare the different curves and you end up with a cutoff. And there's also another way to analyze the data using this J-curve, and you get very similar answers. So you do this for your well and your different lithologies, and you can then go back to your original sort of data, and you can apply that T2 cutoff as well. So now we've got, it's not the clearest of volumes, but there's just a subtle difference change between our bound and our free water in this area. And in this case, the cutoff just changed from 33 milliseconds down to 30 milliseconds. Since you have the cores, you can also calibrate out your coefficients for your permeability equations for your two different equations, and then start working out which one is going to be best suited for your environment. So, you can plot your lab permeability versus your log NMR permeability and solve for your different coefficients. So we then went back and reapplied it to the data, and the original data is the dotted values, and with the revised coefficients are the solid values. And you can see that we've got a general increase, especially in the SDR equation, of a couple of order magnitude jump, and the red Timor codes changed a little bit, but not much. So now we know that the solid red and the solid black curves are going to be our best estimates for our hydraulic conductivity within these areas. So they were able to go from their original resource estimate to a much better, well-defined resource estimate, because the total porosity remained the same, but their definition of movable water or movable resource in this case, because the water was the resource, that increased because our cutoff went lower, but also our hydraulic conductivity increased a little bit as well, which gave them easier access to the resource. So overall, they were quite happy with the results because they were getting more product and with a higher hydraulic conductivity. So that's sort of one way that we can use BMR and some other logs and some coring to get a good understanding of our reservoir or our aquifer or our resource, depending on what segment you're in. So I sort of mentioned as well before that you can start looking at replacing packet tests. So we've got a few different examples where where people have used NMR data to help refine their selection of locations that they're going to test. So instead of testing the full well, they will target particular intervals that they're interested in or want to know more information about for their model. Or, they've gone through the whole process of doing the calibrations and then have worked out that they can replace a large amount of their packet testing with a simple log. So instead of spending a week on a well doing packet tests, they run an NMR log and get equivalent data out of their models. So this is an example that we have here where they ran a series of logs and they were running packet tests, and they wanted to, because time was critical, they didn't want to test everywhere, so they wanted to target particular zones. So they used the Geophysics logs to get a proper depth measurement of the zones that they were interested in. They then conducted their packet tests in those areas. And this was a sort of a long ongoing project. So we went through and sort of did a basic sort of calibration to bring our hydraulic conductivity curves up to match what their packet test results were. And then, because this was an ongoing project, we continually refined this process on multiple boreholes, and we went to a second borehole, applied our calibration values that we determined, and then went to borehole 3. And as you get more and more data, you can start fine-tuning these values in. Cores give the best results but we can go through this process as well. And once you start getting enough volume of data, you can get quite good correlations between log values and packet test results. And we can upscale this data. So it is a continuous log, and we can just average over this area to give us our average hydraulic conductivity over that particular zone. So this is now another beauty of this area of a continuous log. Packet tests you quite well defined to your testing intervals, whereas with a log, we can average over any particular interval that we want to target. And depending on whether you want to do arithmetic mean or geometric mean or a harmonic mean, you can also break out your horizontal hydraulic conductivity or your vertical hydraulic conductivity. And then over time, they started to identify other zones of interest for their projects that they wanted to get more defined information about. So yeah, this is just another example where they went through the workflow, but this time they were interested in the average horizontal and the average vertical hydraulic conductivity for the model. So in a nice layered structure or bed, if you take the arithmetic mean, you get your average horizontal hydraulic conductivity. If you take the harmonic mean, you end up with your vertical hydraulic conductivity. And that's what they were interested in this case. So they did it for both of the STR equations and the Timor-Coates equation. And this is just another sort of quick example here where this company used to do packet tests every 6 meters up the length of the borehole. So these blue shaded boxes. The NMR average data over those same intervals is a thick blue line, and we sort of see a very good correlation between packet tests and our average hydraulic conductivity over the same intervals. There's a couple of zones, like this zone here, where the packet tests are reading a lot higher, and similarly down here. These are on the edges of a well-known formation that is well-known for fracturing. So as soon as they apply the packers, it would fracture and they would get fluid movement around the packer. So it would give a sort of a false reading on the hydraulic conductivity. So there are a lot of hydrogeological sort of examples. The next sort of section, just looked at the time, I probably should speed up a little bit, is some mining applications. So these are sort of like a one-slide look at a couple of different applications. So if your resource is the rock, there's multiple density definitions that the metallurgists use, the resource estimation team use, depending on what segment you're in within the mining industry, you might refer to the density as different things. So the 3 main definitions are in situ bulk density. So your classic gamma density tool measures this because it measures the rock matrix plus the water matrix to give you the in situ bulk density. The matrix grain density is just the density of the pure rock matrix. So if we know the total porosity and we know the bulk density, and the equations aren't here, but you can quickly determine your matrix density. Basically the reverse of using the calculation to calculate density porosity. You can use that to, if you measure matrix, instead of using the equation to calculate density porosity, if you know the total porosity, you can back calculate the matrix density. The other bit of information that is nice to know is this dry bulk density. So basically, if we subtract the volume and the density of water, we can calculate the dry bulk density, which you can start using for your ore assessments, information to feed into your crushers, things like that. So if you know your density and you know your porosity, you can calculate both of these things and get a continuous log of them instead of sending them off to a laboratory. So this is some sort of work in some banded iron formation, and we did the total porosity log. We took some core values, we did some routine core analysis and special core analysis, and we see a generally good correlation between cores and log data that we see through here. This relates also to a good correlation between the permeability and the core values. And the last column here is a dry weight density column. So instead of just doing a few core places, we get quite a nice continuous log of our dry weight density. Actually, just another sort of sample where this time we've calculated a dry bulk density. This is probably a nicer sort of image. So core moisture was critical to these guys. So they would basically take large amounts of core, send it off to the lab and wait months to get their core values back. By taking a density log and a BMR log, which are the green and red lines through here, we can then start calculating a continuous BMR moisture profile, which is the green curve through here. We also did some plug measurements in the black dots, but we see a very good correlation and trend between the wireline log and the core moisture that they got back from the labs. So this is a nice example where, if you collect the correct data in the field, you can start replicating some of the processes that you often do within a lab environment. So I think this is coming up to the last few slides. So this is another example where they went through a dewatering phase. So this chart is quite messy, but on the left is just some gamma ray and magnetic susceptibility measurements. The green bars are some core values, but what we've got is some BMR measurements over a period of time. So the first one's done back in August 2016, and then we repeated them with 2017. So the original data was pre-watering was this high blue line, and we see good correlations between the core values in the lab as well. Then we came back, and after a certain amount of time, they were actively dewatering, and the initial test was for repeatability of the tool. The repeatability was terrible, and after a while we worked out that they were actively dewatering the area, and we were like, that explains why we see this huge difference between the original NMR porosity and the current NMR porosity. And what is also nice about this is where we have this high gamma ray shale unit, our porosities don't change in this zone. They match quite well. And you can start looking at and interpreting if there's preferential dewatering zones. Are you ending up with perched water aquifers and things like that? I don't have an example in this slide deck, but the same principle can be applied to, say, a heat leach pad or a tailings dam, where you can monitor changes in porosity over time. So the last example is on grain size distribution. So I sort of mentioned that the T2 distribution is a pore size distribution. Well, if you have your grain size, and pore size is related to grain size, so the bigger the grain, the bigger the pore, smaller the grain, smaller the pore. If you have a sieve analysis or a laser particle analysis set of data, and you also have some NMR data, we can convert a T2 distribution into a grain size distribution. So instead of this being time-based, it now becomes a metric dimension space. So in this case, from 0.001 micrometer up to 1,000 micrometers. And we start getting an idea of our physical grain size. And this can be important when you're looking at your screen size setting, for example, and if you wanted to optimize your completion. And you can end up with things like your D10, D20, D90 curves that give you the probability of certain particles under a different size. And this is useful in either a completions setting, or if you're interested in knowing the grain size distribution for geotechnical assessments. So hopefully that gave you enough sort of information of some examples that we've been involved in over the last 4 or 5 years. The tool is just a shiny metal tool cylinder, and we've got a couple of different models depending on borehole size and things like that, and we have to choose the correct tool required. To deploy it, it can go on any sort of wireline truck. Your local wireline company can help you out with that, and it's a nice safe tool. It's just a couple of strong magnets, and we don't have to worry about radiation or anything like that. And yeah, to summarize, BMR gives us a unique framework and a great way to integrate all of our other data streams, density, salinity, to give us a nice, good, clear image of the formation underground. And whether you're in a groundwater resource, or brine or solution mining, or even a hard rock mining, wherever there's water is an issue, either too much or not enough, you can start help defining that to get a better understanding of your formation and help clarify your resource as well. So that is pretty much that from me. Is there any questions?
Well, thank you very much, Benjamin. It was great, great overview of the method, and it's always amazing. We usually deal with airborne data or ground data, right? And everything has such poor resolution compared to downhole. So it's quite amazing. Yeah. So if anyone has questions for Benjamin, I don't think we have the chat option anymore available, but feel free to just unmute yourself and turn on the camera one at a time. Though we don't want to clog the internet. So yeah, if anyone in the room has a question, feel free to chime in. I see that Richard Smith has his mic unmuted. Richard, you have a question?
Yeah, Benjamin. I think we've got an idea about how these downhole tools work, but maybe you could just explain what's required in these packet tests that you're talking about, so people can get an idea of the logistical differences.
So there's when it comes to bore testing, there's a couple of different options. So there's things like packet tests, slug tests, or pump tests. So a packet test, depending on the setup, also known as a drill stem test, basically they lower a device down the well, they will set a couple of plugs or packers, and they will inflate them above and below a particular zone, and then they will either inject or extract water over a particular length of time, and they will watch how the formation responds. So if it's a very low permeability zone, they might have to pump for a very, very long time to get a response out of the formation. And then from that drop in head and the time, they can back calculate a hydraulic conductivity. So from an operational point of view, this often has to be done on a rig. So rig time is expensive, and packet tests can typically take from a few hours to days. And you also have to do something with that water. So I sort of showed you that process of calculating the salinity of the water from the aquifer. Here in Australia and Canada is probably the same. You have very stringent rules on what you can just pump out onto the ground. So if it's below a certain salinity, they can just flow that onto the ground or into a crop. If it's above a certain salinity, then they have to like pump it into a water tanker and ship it off and go get it treated. So it can help in a couple of different ways, the data. So you can use it to quickly determine what your salinities are going to be to help decide on treatment of your extracted water for a pump test, or you can just use it to help potentially replace that pump test as well. Did that answer your question, Richard?
Yeah, that was good. Thank you very much.
Yeah.
Hi, Benjamin. Doug Oldenburg here. Nice talk. Enjoyed it. I have one question. It has to do with basically the charge-up time, T1. Is there any really interesting information that one can get by looking at what goes on in the on time?
Yes. So when it comes to a nuclear magnetic resonance measurement, we can either measure T1 or we can measure T2. So beauty of T2 is it's a fast measurement. So we just wait a certain amount of time and then we do our what we call a CPMG sequence, named after the four guys that mentioned it, and we get actually, can I go to that slide? Well, you basically end up with your decay. That looks something like, way back at the start. Yeah, so we end up, we measure this. So this is a quite relatively quick measurement. So we just normally have to wait 3 to 4 seconds, and then we do this sequence and we do sort of 1,000 echoes at your echo time. So we can do that repeatedly quite fast. If we want to measure this T1 time, we can do it, but what we have to do a series of measurements where we wait a certain amount of time, do this red curve measurement, wait a bit longer, do it again, and we slowly build up this curve. So it's a lot longer measurement. And you can do it downhole, you just need a much slower logging speed. You can also get total porosity from that. There are differences in the relaxation measurement, relaxation mechanisms between these two. So T1, I don't have a diagram of it here, but let's start with T2. So the main drivers for the relaxation for our spin relaxation is a combination of our pore volume, which I said before. So if the spinning protons interact with sort of like an ion atom, it will dephase it quicker. So that is one mechanism. You have bulk relaxation, so just the general tumbling of your water molecules in the pore space and interacting with each other will slowly decay as well. And then also diffusion. So if we have small changes in magnetic field from one side of the pore to the other, then that also has an effect on how quickly this dephasing happens. But we design the tools such that the diffusion is quite small and water is uniform as well, so it can be negligible. And our bulk relaxation, because we're typically in small pores, is also quite small as well. So that's why we sort of not push, but we assume that our main drivers are our pore volume size that drives this relaxation. T1 is mainly driven by bulk relaxation and our surface relaxation. It has no effects on the diffusion relaxation mechanism. So it's a good way of, if you're interested, you can start getting an estimation of how much diffusion is in your environment. So yeah, so you can do both. You can measure T2 and T1 relaxation times, and they both give you, well, they both give you total porosity in the end, and they both give you information about the formation. Transverse relaxation, or your CPMG measurement, is just a lot easier and quicker to measure downhole. So instead of your log being, so for T2, our logging speed is typically 1 meter per minute. For T1, it will be a lot slower than that.
Okay, thank you. I appreciated that.
No worries.
Anyone else has a question for Benjamin?
Two questions, Benjamin. One is whether or not there's any borehole diameter correction that needs to be made. And the second was, I didn't quite understand how you can get both the vertical and the horizontal permeabilities. Is it basically you're kind of averaging the permeability as you go up and down the hole to get the vertical permeability?
Yep. So the last question. So when you're, I don't have easy access to the slide. So basically, when you're averaging, so if we think of a nice layered formation where we have layers, on top of each other like this, if we do the arithmetic mean, we end up with our average horizontal hydraulic conductivity. Have you seen that in the image? If we do the harmonic mean, because your harmonic, you take the inverse of the, you end up taking the inverse of the values that you're averaging. So a low permeability zone will have a bigger impact. So water going in a vertical direction, if this is a low permeable barrier, will be driven by this. So you, so in a layered formation, if you take arithmetic mean, you get your horizontal hydraulic conductivity, and you can just average the values up in your zone of interest. And if you take the harmonic mean, you get the average vertical hydraulic conductivity. If the formation is very anisotropic, so very random, then you just use the geometric mean, and that is the same for horizontal and vertical hydraulic conductivities. And what was the first question again, sorry?
Oh, just whether or not the variations in the borehole diameter have any significant effect.
No, so as long as the borehole so as long as the borehole is less than our sensitive shell, then we don't get any signal between what's between the tool and that shell. So as long as the caliper reading is less than our diameter of investigation. So our main two diameters of investigation are 230 millimeters and 360 millimeters. So we typically like sort of a 20 mil into the formation measurement to just help avoid some of the borehole drilling damage that may come through. But yeah, we just measure a thin shell into the formation. So yeah, as long as there's no washouts into that area, then we get a measurement of the rock matrix.
Thanks. So similarly, I guess there's no effect from plastic casing or not plastic casing.
Correct. So yeah, PVC or fiberglass casing is fine. We just can't operate in a metallic environment.
Great, thank you.
Benjamin, this is Randy Enkin.
Hi, how are you?
Can you hear me?
Yes, yeah, yeah.
What is the dependence on magnetic materials in the rock, in particular magnetite?
Magnetite is a big no for us. Hematite we have successfully logged in. So once you start getting into your ions, your echo time has to be a lot faster. So we have a special tool that we can get down to a echo time of 250 microseconds. And this starts correlating well with what we've seen in the lab measurements as well. So magnetic susceptibilities less than 500. I always get the units confused on this, 500. I would have to confirm, I forget whether it's CGS or SI units. So anything less than 500, there's no effect. 500 to 1,000, you need to start paying a bit more closer attention to the detail and the data. And then once you're above
imagine that's 10 to the minus 6 SI.
Yes.
Probably 10 to the minus 6 SI.
Yeah, yeah. It's written on my board of work because I forget the units every time. But yeah, I can, well, if you send me an email, I can confirm whether it's CGS. It's either CGS e to the -3 or SI e to the -6. I think.
And you just reject data when it's higher?
Basically, yes. Yeah. Yeah. So once we're into magnetite, it just throws everything off completely. So it's pretty much impossible to measure in magnetite, unfortunately.
Thank you, Randy. So we're just past the hour, unless someone else has a burning question and wants to ask it now. Otherwise, I'm sure we can contact you on your email address. Thank you, everyone, for exactly. Thank you, everyone, for coming again. I apologize for the sound was a little bit over the place today, but we'll do better next time. Benjamin, thank you again for your time. I hope you have a wonderful day in Perth, and we'll see you soon.
Yeah, all right, sounds good.
Okay.
I can get back over there when travel restrictions lift.
I guess so, yeah. Good luck. Stay safe, everyone. Okay, bye-bye.
Cheers. Thank you. Bye.